Hello, this is the second part of the chapter 1.8, and we will work through several examples of matrix transformation. So, and just to remind you that in last mini lecture, we defined a transformation T of X, which transformed n-dimensional vector X into the m-dimensional vector B. And we usually call the resultant vector an image, and the dimension of our vector X we'll call domain, and the dimension of our resulting vector B we call codomain. And the size of the image space we refer as a range. So we use this terminology to work through several examples of transformations and try to figure out how we can find vector X if B is given, how to find B if X is given, and how to figure out if our transformation is actually unique. Okay, let's start from the simple vector A and define the transformation A from R2 to R3 using multiplication by matrix A. Or we can say that our transformation T of X is equal matrix A times vector X. Okay, so we can start with a definition of our transformation and just write it down exactly as it is. We multiply in vector A, matrix A by vector X. What vector X? Any kind of two-dimensional vector. How do we know that it's two-dimensional? And this is where our definition of transformation has to be useful. So we're given this information from the problem that we transform in two-dimensional space to three-dimensional one. So our vector X coming from R2. Okay, so let's rewrite our matrix A and multiply it on arbitrary vector x1, x2. Then we perform multiplication matrix by vector, and we get a set of 3 linear combinations which will define our transformation. And we know that we are on the right track because we know that transforming R2 to R3 and our resulting vector, our image, has 3 components. So that must be a good sign, but also always check yourself, never just try the dimension. Okay, let's just go ahead. And so this is for any arbitrary vector x1 and x2. What if we are given very specific vector u? For example, what kind of image that specific vector produced if we apply the transformation T? And again, we start with the explicit definition of our transformation as a matrix multiplication. We take our matrix A and multiply it by vector U. So let's rewrite our matrix and multiply it by vector U. Then we follow the rules for matrix multiplication by vector, and we'll get the specific vector 5y9, which is our image. And again, we're going into the 3-dimensional space, so 3 components should be all right. Okay, so now what if we are given an image and we're looking for the vector X which produces this image? Let's see how we can deal with that problem. So in question 3 here, we are given the image, 3 component from vector B. And what we're looking for is a 2-dimensional vector X, which when multiplied by matrix A will give us this vector B, or whose image is under transformation T is vector B. And again, we start from the definition. We apply transformation T to the vector X, and we should get a B. So in other words, because our transformation is a matrix multiplication, we can form these questions as the solving the matrix equation AX is equal B. So we will explicitly write our matrix A, multiply it on the vector x with two arbitrary entrants, x1 and x2, and we should get our vector b. And we're trying to find the solution. So, and we already did it like probably hundreds of times in this course. So we know that the best way to approach to the solution is try to write down augmented matrix and then reduce it to the echelon form. So we identify the pivot column and first pivot column, and then we reduce the second column to the pivot form, which gives us a reduced echelon form, which is very convenient because we can use the first row to write down solution for x1, second row solution for x2. So we can actually explicitly write down the vector x, which give us the vector b under the transformation. And this is specific vector 1.5 and minus 0.5. So we know that when we apply our transformation t to this vector, we guarantee to get the vector b. Now the question is that the only vector which is x the only vector which give us a b, or there is many, maybe that three-dimensional vectors when applied to the matrix will give us a vector b? Let's just try to think about it. When we are trying to find our vector x, we are solving a matrix equation. And again, here I just basically rewrote our matrix equation. So, and when we reduce this equation to the echelon form, we had a pretty neat matrix which has in both variables has a pivot columns, and the third row is equal zeros, which is, according to uniqueness theorem, give us a unique solution for x, which means that there is only one x whose image is desirable vector b, or we often say that the image b is unique. So there is basically only one vector x which give us vector b under the transformation t. Okay, and that's all about examples, and next time we talk about the matrix transformation.